Okay friends, before we get into problems, I would like to just give you broad guidelines of how you must approach a problem. The first thing a student must do is to assess the context in the sense that you must know, of course you are in Laplace transforms, but you must know whether it's a direct problem or something based on a property. For an exam like this that we are talking about, I don't think any examiner would think of giving fundamental questions. He would always be looking at how to test the deeper knowledge which is available. So first, you assess the context, right? What I mean is it a direct problem or based on a property? Of course, there are many problems which can be done by more than one property, as we have seen in the case of the unit step function problems. So there can be more than one property. So is it a direct problem or some properties are involved? Recall the property or the properties. What we want ultimately is the fastest way to solve the problem. Now it all depends on you, because if you get into direct way of solving where no properties are involved, you may end up integrating very big functions, and integration can become really a very big problem if you are not strong in the various techniques of integration. Instead, the chapter is enriched by several properties which are available. So the fastest way to solve will be through properties. So you must have a very good hold on the properties. So I think before we start problems, we must keep these 3 points in view. Now as I take problem by problem, this is exactly what I'm going to tell you. What is the context, which property can be applied, and what is the fastest way to solve. Of course, wherever there is more than one alternative present, I will try to show you all of them, and it is for you to choose which is the best. So let us begin the first example. My first example is I know every BTech student can do this problem, but let us see how we can do it using a gamma integral, for example. Now we can write this as Laplace transform of t power minus half. Refer the tables, and you will write gamma minus half plus 1 by s to the power of minus half plus 1. So this is gamma half by s to the power of half. You know gamma half is root pi, and this is root s. So it is root of pi by s. Correct option is B, as you can see. Problem number 2. Another direct problem. Expand the numerator. Simplify. Apply linearity. And you will get gamma 3 by 2 plus 1 by s to the power of 3 by 2 plus 1 plus 2 times gamma half plus 1 by s power half plus 1 plus root of pi by s, because this was done just in the first example. Now gamma 3 by 2 plus 1 will be 3 by 4 root pi by s power 5 by 2. Gamma half plus 1 will be half into gamma half. So therefore half and 2 will get cancelled. You will get root pi by s to the power of 3 by 2 plus root of pi by s. So if you simplify this result, we will find that root pi can be taken common. 3 by 4 s power 5 by 2 plus 1 by s power 3 by 2 plus 1 by root s, and the correct option is A, as you can see. So a very simple way of solving this problem. Let's go to the third question. Now this problem can be solved in two different ways. One, if your memory is sharp, you can directly use a formula which I'll first mention. Laplace transform of t cos hat is s square plus a square by a square minus a square whole square. So this exactly fits into this context. So therefore the answer to this problem would be s square plus 4 by s square minus 4 whole square. So the problem is straight away solved if you know the property. But what is the second method? You write the definition of cos h2t as e power 2t plus e power minus 2t by 2. Okay, definition of cos h2t. Then you apply linearity, t e power 2t plus t e power minus 2t by 2. Now if you remember formulas, the Laplace transform of t e power at is 1 by s minus a whole squared. So the transform of t e power 2t can be written using that, and the transform of t e power minus at would be 1 by s minus a whole squared, s plus a whole squared. So the transform of this and transform of this can be directly written. So if you take this with reference to those two properties, you will have half 1 by s minus 2 whole squared plus 1 by s plus 2 whole squared. Now what you need to do is just simplify this. If you simplify this, and you will get s square plus 4 by s square minus 4 whole square. The same thing you will get. I am not showing you the details because it's only taking LCMs and other things. But you can easily see method 2 is longish. We have to go through, these two formulas. Whereas this is a direct situation. If you can prepare a decent table of transforms of all standard situations, I think you can save lot of time. After all, managing time is very essential in these exams, because you have to reserve time for the tougher areas where you may not suddenly get brilliant ideas. You may have to spend longish techniques, and for that you need time. So wherever you can save time using properties and memory, I think you must really be able to manage for the bigger situations. So as you can see, we have these two methods, okay, and the answer will be the same in both the cases, and you'll observe that option D is the correct option for this problem. Question number 4. Given the Laplace transform of J0t, J0t is the Bessel function, what is Laplace transform of J0at? Friends, remember that getting this formula itself is extremely difficult. So assuming that we are not going into the details of how this was obtained, but getting this from that, it's a matter of just 2 steps. So this is not a direct problem. This is based on a property. Which property is involved? You're all aware that there is a property called the change of scale property. Okay. Let the Laplace of J0t, which is 1 by square root of s square plus 1, is equal to f of s. That is, we are calling this f of s. So Laplace transform of J0at is 1 by a f of s by a. So you have to replace s with s by a, and don't forget to multiply with 1 by a. So in this output, you introduce a 1 by a because that is required, into 1 by square root of s by a whole square plus 1. Right? So the property has been applied. Simplify and you will get 1 by square root of s square plus a squared. So the Laplace transform of J0at is 1 by root of s square plus a square. In fact, students, remember this directly. Even this can be avoided, but it is only to tell you how properties can be used in case you forget. Otherwise, you can prepare, as I told you, a very decent list of all standard Laplace transforms. And normally in engineering colleges, this J0at transform is always remembered. Particularly EC students use it in communication engineering. So therefore, I think this should be remembered by all students. This is only a backup method by which you can still solve it. Correct option is B. Question number 5, a very interesting problem. I hope you remember this integral is a convolution integral. It's a convolution integral. Convolution of what functions? It is t square and e power t. Please go back to the old lecture and refer. The convolution of this is this. So therefore, this is nothing but Laplace transform of t squared into Laplace transform of e power t. Convolution theorem says that. Of course, it's commutative. You can write it any way you want. So this is nothing but 2 by s cube into 1 by s minus 1. So 2 by s cube into s minus 1. So very simple, otherwise you land into problem. The correct option is D for this. for students who are not aware of this technique, will get trapped in expanding this, multiplying this. You'll get 3 terms, and then you have to integrate that, and then you have to take transform using linearity. That would eat away more than 10 minutes of time. So see how your properties are helping you in solving problems. So many people get scared when they see these type of situations. They feel some integration is involved. No, it's after all a convolution integral. But don't forget, the limits must be 0 to t. If you notice that 0 to t, then almost get convinced that it is based on the convolution integral. Once convolution integral is given, the answer is going to be very, very fast. Okay, so this was selected only to explain how to react when a convolution integral appears. Okay friends, I've already illustrated this example. However, let me once again give it back to you. You are given a signal, right? So we have already seen this example, but I would like to once again do it for you. So this f of t is 5 times ut of 2 minus ut of 4. So the Laplace transform of this is 5 times e power minus 2s by s minus e power minus 4s by s. So it is simply 5 by s e power minus 2s minus e power minus 4s. You know that we can also integrate and reproduce the same result. The correct option for this problem is A. The 7th question. There is a function which is defined like this in 2 different intervals, 0 less than t less than 2 and t greater than 2. So this is a function. Of course, it's continuous at t is equal to 2. So if you want the Laplace transform of this, you can integrate from 2 to infinity e power t minus 2 e power t dt. I've used only definition, and to integrate this, it is better you make the limits 0 to infinity. That becomes convenient. Actually, there is a small correction. You write it as e power minus st if you follow the definitions, right? So what you do is, you introduce a small substitution, t minus 2 is equal to u. So the limits will change. The limits for u will be 0 to infinity, e power u, e power minus s, and t can be replaced with u plus 2, right? Because the integration is on the variable u, we can take out e power minus 2s outside. So we'll have e power u into e power minus us. You'll have like this. So when you actually integrate this, what will happen? E power minus 2s integral 0 to infinity e power minus u into s minus 1 du, right? So if you integrate that, e power minus 2s into e power minus u into s minus 1 by minus of s minus 1 0 to infinity, right? So what will happen if you apply the limits? When u takes the value infinity, this becomes 0. So the upper limit produces nothing. So we'll have e power minus 2s 0 minus 1 by minus of minus is plus, because there's a minus here also. So you will get this. So it is e power minus 2s by s minus 1. So the correct option will be C for this problem. But the question is it the only way to do the problem? Of course, if you are good at second shifting property, you can also do it directly. Okay? But this is quite fine. Only thing is you must be able to do it quickly. In the 8th problem, we have a function a discontinuous function you can easily see the graph. So we have a 1 to 2 interval, a 2 to 3 interval, 1 to 2, 2 to 3. K is some constant. In the interval 1 to 2, it's a constant function. So let us say k units. And the interval 2 to 3, there's a jump, double the height, 2k. So you can say sort of a staircase, right? Now for this, how do you get the transform quickly? So you can write f of t for this interval. This thing can be written as k times u1 of t minus u2 of t. Then for the next one, it is 2k times u2 of t minus u3 of t. So it has all become simple now. I am now writing directly e power minus s by s minus e power minus 2s by s plus 2k times e power minus 2s by s minus e power minus 3s by s. It's done. The problem is done. It's only the question of combining them properly, and the correct option for this problem will be D, which you can easily verify. So the 9th question, we want to find the Laplace transform of 1 star 1. So using convolution theorem, you have to simply compute Laplace transform of 1 into Laplace transform of 1. So it is 1 by s into 1 by s, which is 1 by s squared. So the correct option will be C. However, students can also write the convolution integral for 1 star 1 and then find out in the normal way through integration and still get the same result. So it is always advisable to keep properties with you so that we get the fastest way to get the answer. I've already told you in the guidelines that first assess the context, remember the properties, and look for the fastest way to approach the answer. Question number 10, another similar problem. The transform of cos t star sin t. Again, apply convolution theorem, transform of cos t into transform of sin t. Refer tables. So it's all pretty simple, no integrations involved, and the correct option is B. In the 11th question, we have selected the unit step function. The problem is Laplace transform of u1 of t star t. Friends, please observe that I am focusing continuously on the convolution problems because this is one of the hot areas for testing. So, Laplace of u1 of t into Laplace of t. So, this is the Laplace of unit step function. So, you write e power minus s by s into 1 by s squared. So, e power minus s divided by s cube. So, the correct option for this problem is A. Let's first see the question. Given f of t is equal to f of t plus 2, what is Laplace transform of f of t? Friends, I hope you know the moment you read a statement like this, f of t stands for a periodic function. So, note f of t is periodic with period capital T is equal to 2. So, this is the period. Fine. Now, all of us know we have a property in Laplace transforms based on periodic functions by which we can directly write the Laplace transform. So, what does the formula say? Let me write it here for you. The Laplace transform of f of t, of course, f of t should be periodic with period capital T, in this case 2 of course, is 1 by 1 minus e power minus st. Please observe it is not small t but capital T, integral 0 to capital T, again that's a very important thing to remember, not infinity, e power minus st into f of t dt. So, this is a formula. So, apply this formula to this context with capital T is equal to 2, and what do you get? Answer 1 by 1 minus e power minus 2s integral 0 to 2 e power minus st f of t dt. So, it is a straightforward application, but unless you are in touch with all the formulas, you will not be able to recover this. Remember, a small variation of 1 or 2 marks can alter your fate. Instead of landing into a good IIT, you may not get an admission at all. Okay, so just be watchful. Correct option is A. Question number 13. Laplace of sin t minus pi into ut pi. Again, there are two options. One is you write the meaning of this function using the definition of the unit step function and then use integration. But this problem has been designed on the so-called second shifting property of Laplace transforms. So, this is based on second shifting theorem. So, I am writing for you, for your reference, the second shifting theorem. Laplace of f of t minus a ut of a is e power minus as into f of s. So, what is f of s? This is the Laplace transform of f of t. Now in the present context, you can see these two are comparable, right? So a is equal to pi. So here a is equal to pi and f of t is sin t. So what will be f of s? It will be 1 by s squared plus 1. And what is the answer? The answer is obtained from here. So the answer will be e power minus pi s by s squared plus 1. Right? F of s is 1 by s squared plus 1 and e power minus as f of s will give us this particular result. The correct option is B. The 14th question is again based on the second shifting property, but this is not straightforward. The question is, what is the Laplace transform of t into u1 of t? Please observe, in the second shifting property, we require f of t minus a ut of a. So here a is equal to 1, but this function is still not ready. It has to be processed to use the second shifting property. So what you do is, you subtract and add 1. Be careful not to add and subtract, but subtract and add 1 into u1 of t. So you can break this by linearity into two separate transforms. Now we know the transform of u1 of t is direct, so you can write it as e power minus s by s. That is straight away coming from tables, and this is based on second shifting property, right? So if you look at this, this looks like f of t minus a into ut of a. So you can see what it is. So what is a equal to? 1. And what is f of t? It is t. So what is the output of this? It is e power minus as into f of s. So what is f of s? Transform of t, which is 1 by s squared. So you use this formula for this context and you will get e power minus s by s squared plus e power minus s by s. So if you simplify this, you will find that the correct option is A. So this is how second shifting property will be used for slightly typical situations. The 15th question, the problem is, now if you observe this problem carefully, two properties are involved. One property is division by t, and because you are multiplying with an exponent, the first shifting theorem is also involved. So what do we do, right? So our note is two properties involved. One, division by t. 2, first shifting theorem. These are the observations. So if you have identified the properties, then getting the result is just a matter of time. So where do we start? First, pick up sin t. So write Laplace transform of sin t as 1 by s squared plus 1. You call this f of s. Student has got two options. He can take up first shifting followed by division, or division followed by first shifting. My preference is you first finish the division part. Laplace transform of sin t by t is integral s to infinity f of s ds. So integrate 1 by s square plus 1. Don't forget the limits are s to infinity. So it is s to infinity 1 by s square plus 1 ds. Any student can do this integration. And what will you find? You will find it is tan inverse s from s to infinity. So when you apply the upper limit, you get pi by 2 minus tan inverse s. So what is the output? Cot inverse s. You call this output g of s. So what did we do so far? We have used this property. Shifting is still remaining. That is because we are multiplying with an exponential function. So Laplace of e power minus t sin t by t is simply shifting on the s scale. So g of s plus 1. So what is the output? It is cot inverse s plus 1. You would get the same result whether you come through shifting first then followed by division. We have done division first and then shifting. So cot inverse s plus 1 will be the option, and the correct answer is B. In the 16th problem, once again we have the division by t situation. The problem is the Laplace transform of e power at minus e power minus bt divided by t. So this is based on division by t. So the approach is very simple. First take the numerator, find the transform, call this f of s. Of course, you must be careful not to take LCM and combine them, because that would lead to complicated situations in the next stage of the problem. So don't take LCM. So Laplace of e power minus at minus e power minus bt by t is integral s to infinity of 1 by s plus a minus 1 by s plus b. Integration is straightforward. What do you will get? Log of s plus a minus log of s plus b. Of course, limits s to infinity, log of s plus a by s plus b, s to infinity. Of course, you cannot directly apply the limit infinity because you get infinity by infinity situation. L'Hospital's rule is there, but you can easily see that you have to just invert this fraction in this context, and the answer will be log of s plus b by s plus a. This almost happens in all the division by t problems, and the correct option for this problem is A. Friends, I have chosen one more problem on division by t. The problem is to find the Laplace transform of sin square t by t. Right? So, first begin with the numerator. All of us know we cannot do this directly. Using the basics of trigonometry, you first convert sin square t. Apply linearity. Laplace of 1 is 1 by s. Laplace of cos 2t is s by s square plus 4. We will call this f of s. Now we are ready to apply the division rule. So Laplace of sine square t by t is integral from s to infinity f of s ds. So you will integrate this within the limits s to infinity. So we can write this as half integral 0 to infinity 1 by s minus half into 2s by s square plus 4 ds. This is just to manage the integration there, okay? And what do you get? Half log s minus half log s square plus 4, right? So we can write this nicely as half log s by square root of s square plus 4 from s to infinity, right? And as I told you, invariably in all these problems, you can just invert this fraction in the logarithmic situation and leave it at that. So this is how you can apply the division rule for slightly difficult problems also. So what are the steps? Sine square t not transformable, change it using trigonometry, use linearity, get the output for the first stage, then integrate that from s to infinity, manage your logarithms carefully, and then you get this result. The correct option for this problem is D. Friends, this is a nice problem. It is not a Laplace problem. Basically, it is an integration situation. Integral 0 to infinity sine t by t. Well, we have the experience of solving these problems because it was already explained in the context of improper integrals. But I would like to just give you a very important idea using Laplace transforms. Integral 0 to infinity, I'll give you two rules for your convenience. F of t dt is equal to the Laplace transform of f of t evaluated at s is equal to 0. That means you find the transform of this, and you know the output will be a function of s, put s is equal to 0. You got another rule, 0 to infinity e power minus at f of t dt is Laplace transform of f of t evaluated at s is equal to a. So students can use these two rules very effectively while handling improper integrals. Of course, what I mean is a type 1 improper integral, right? Type 1 or type 3. So we are here right now. So what we will do, you find the transform of this and then put s is equal to 0 in the final output. So what are the steps involved? Find Laplace of sine t by t, to answer is equal to f of 0. So transform of sine t by t is cot inverse s, right? Answer is equal to, suppose you call this f of s, answer is equal to f of 0. So cot inverse of 0 will be pi by 2, and the correct option is B. So this is a very quick way of solving this problem. Friends, the 19th question that I have chosen is another improper integral based on the same idea. The problem that is given to you is integral 0 to infinity t e power minus 2t cos 3t dt. Well, I would like to do this problem using the two rules that I just gave you. So first what you do is you target this pair, right? So the Laplace transform of t cos 3t you first determine. So for your reference, the Laplace transform of t cos at will be s square minus a square by s square plus a square whole squared. Use that in this context and you will get s square minus 9 by s square plus 9 whole squared. You call this f of s. So we took this function t cos 3t, found the transform. Now 0 to infinity t e power minus 2t cos 3t dt will be f of 2. This is what we have to pick up, right? So replace s with 2. 4 minus 9 by 4 plus 9 whole square minus 5 by 13 square is 169. So the correct option happens to be C. So this is how improper integrals through Laplace transforms can be one of the fastest way of evaluation. Friends, 20th problem is based on a similar idea. The problem that we choose will be integral 0 to infinity 3 power minus t cos 4t dt. Well, the only challenge is to convert this into an exponential function. So 3 power minus t can be written as e power minus t log 3 into cos 4t dt, right? So you will note a power minus t is equal to e power minus t log a. So what's the approach? You first find the transform of this Laplace of cos 4t is s by s square plus 16. Call this f of s. Therefore, integral 0 to infinity e power minus t log 3 into cos 4t dt will be f of log 3. So you have to just replace s with log 3. So log 3 by log 3 whole squared plus 16, and this is the answer. And the correct option for this problem is D. With this problem, we come to the end of some illustrations of the Laplace transforms. We now embark on the inverse Laplace transform for the next set of problems.